Our planet has existed for over 4.5 billion years and is expected to last for at least about the same amount of time, perhaps even longer, depending on how the red giant phase of our sun goes down. However, when it comes to conditions suitable for life, they may come to an end much sooner. But when it comes to the existence of Earth itself, we can imagine a scenario in which Earth ceases to exist much earlier. Let's say an unknown black hole or neutron star enters our solar system and gets too close to Earth. It could tear it apart due to tidal forces. Most likely such an event will never occur, but it's not completely impossible. And the universe has ways to get rid of our lovely planet. But are there ways to get rid of the entire universe? Generally, when speaking about the death of the universe, several familiar scenarios are mentioned. The Big Crunch, a process opposite to the Big Bang. In this scenario, the expansion stops and the universe begins to contract back to a state of an infinitely dense point. The Big Rip scenario, where expansion continues until distant objects become invisible to us, and then ultimately expansion tears apart galaxies, planetary systems, and eventually even atoms. And of course, the heat death of the universe. Here expansion also continues, but it's not that dramatic, with no particle tearing. Stars die out, then black holes evaporate, leaving behind an infinite dark cosmos without any structure and objects. Which specific scenario is correct depends on the properties of the universe, and currently the heat death scenario is considered to be the most likely. However, whatever the outcome, it is so far in the distant future that it should not really bother us. Yet another scenario by which the universe in its current form could cease to exist is called false vacuum decay. There is a non-zero chance that it could happen right now. Though it is more likely that if it were to happen, it would be in some distant future, but there is also a chance that it has happened already. Let's get into what vacuum are we talking about, why it's false, how it decays, and why and how it could potentially destroy the universe. My name is Andrei, and this is Cosmos Elementary. So here's the problem. It's not impossible that the vacuum in our universe is not true vacuum, but rather a false one. And there is a chance that somewhere in the universe it will spontaneously transition into a state of the true vacuum. That is what is called false vacuum decay, and it could destroy the universe as we know it. Right now it's probably not very clear how that could happen. First, we need to understand what we mean by vacuum. In general, this word can refer to quite different things. Some might say there is vacuum inside a chamber from which the air has been pumped out, but that wouldn't be true or even high vacuum. It's more like just very low pressure. Even in laboratories, the vacuum that scientists create isn't perfect. No device currently has the capability to pump out every single atom from a container due to the imperfections in the equipment and various effects. To get close to the perfect vacuum, you would need to go to space, but space is kind of a big place, and conditions there vary dramatically. Lower Earth orbit is space, but it still contains the Earth's atmosphere, which has noticeable effects. Due to friction with the atmosphere, satellites gradually deorbit unless their trajectory is adjusted using thrusters. There is still some regular matter even in the interstellar space, and perhaps the least amount of it is in intergalactic space. There, a volume of a cubic meter can contain not a single atom of normal matter. But all that is emptiness in a, let's say, regular, everyday sense. However, today we are interested in something different. Let's imagine that we made a container and we managed to somehow remove from it every single particle and also all of the radiation. Could we call what's inside absolute emptiness? According to how modern physics views particles, the answer is no. One of the most successful theories that describes our reality is quantum field theory. According to this theory, fields permeate throughout the entire universe. and at every point in space, they have some certain value, which can change over time. In quantum field theory, particles are not just super tiny balls of matter, as we can usually see them in illustrations. Instead, they are oscillations or excitations of those fields with different energies. Each type of particle is associated with its own field. For example, photons are excitations of the electromagnetic field, quarks are associated with the quark field, and gluons with the gluon field, and so on. So if we remove all these excitations from a volume of space, which we want to make as empty as possible, the fields themselves will still be there. The oscillations of fields can have different energy levels, and there is a minimum possible energy level. The situation when we would normally say that there were no particles, and it would be called quantum vacuum. But still, even in this case, it is not completely correct to say that this volume of space is absolutely empty. Even when fields are in their minimum possible energy state, they still exhibit slight fluctuations as dictated by Heisenberg's uncertainty principle. These are quantum fluctuations that many of you have probably heard of. In these fluctuations, at very small scales and over very short periods of time, pairs of virtual particles constantly appear and disappear. In other words, even in a region of space that is completely empty in the usual sense, at the quantum level there is still some energy which is referred to as zero-point energy. The idea of quantum fluctuations is not just theoretical. For example, there is an effect called the Lamb shift. This effect was first measured in 1947, and without going into too much detail, the essence of it is that it was predicted that electrons in hydrogen atoms at 2s and 2p energy levels should have the same energy. However, the Lamb and Rutherford experiment showed that these energies are in fact different, and that became known as the Lamb shift. And less than a year later, Hans Bethe explained this shift by proposing that the electron was interacting with those quantum fluctuations or virtual particles. In other words, we observe a real effect of vacuum energy. Another popular example is the famous Casimir effect predicted by Hendrik Casimir in 1948 and later confirmed in experiments. According to quantum field theory, even in a vacuum, in its minimum possible energy state, fields fluctuate, and virtual particles can spontaneously appear and disappear. These quantum fluctuations are a fundamental aspect of the theory. In the case of electromagnetic field, it is virtual photons, which could have all of the possible wavelengths. When you place two uncharged parallel mirror plates very close to each other in a vacuum, waves of certain longer wavelengths basically wouldn't fit between the plates. So virtual photons with longer wavelengths cannot exist between the plates. That creates a difference in pressure between the inside and the outside of the plates. This pressure difference causes the plates to be attracted to each other, resulting in the Casimir effect. This effect has been confirmed in experiments multiple times, providing strong evidence for the existence of quantum fluctuations and vacuum energy. In 2018, an article was published in the journal Nature Physics about an attempt to create images of quantum fluctuations. Scientists used superconducting quantum interference device, and it seems that quantum fluctuations manifested themselves in the data as noise. Also, research conducted by scientists working with LIGO gravitational wave detector suggested that quantum fluctuations can even have an effect on macroscopic objects. It was predicted that quantum fluctuations could influence the mirrors of the detector, and indeed, this effect has been measured. If there is displacement of mirrors due to quantum fluctuations, it is tiny, orders of magnitude smaller than the size of a hydrogen atom. But those measurements had some practical use as well. Taking these effects into account, we can enhance the detector's sensitivity. And that's not all. When discussing vacuum energy, it's hard to forget about dark energy, a mysterious form of energy that appears to be causing the universe to expand at an accelerating rate. We don't know what it is, but we observe its effects. Often when describing it, you might hear something like energy intrinsic to space itself. It does sound quite similar to what we've been discussing. vacuum energy or zero-point energy. And it is indeed one of the potential explanations for dark energy, although not the only one. But there is a problem with this option. It's actually one of the biggest challenges in modern physics, which I briefly mentioned in a recent video about the fine-tuning of the universe. Something about the predicted value of the cosmological constant being many orders of magnitude larger than the measured value. One could say that taking into account what quantum field theory describes and the uncertainty principle, the input of a single virtual photon is small. But if we add up all of the frequencies, it begins to approach infinity. But even if we set the limit of the Planck energy, there should still be too much energy in the cubic inch of space. And if you look at the amount of energy required to explain the observed accelerated expansion of the universe, it is 120 orders of magnitude smaller. Despite the fact that in many other aspects quantum field theory provides excellent descriptions of various aspects of our universe, we still have to grapple with this problem. Speaking of emptiness, which is not really empty, we have to mention the Higgs field. That famous field, which like other fields permeates the entire universe, and interacting with it, elementary particles like electrons and quarks are supposed to gain mass. And now the Higgs field stands somewhat apart. While for most fields, the so-called vacuum expectation value, or the value expected in a vacuum state, hovers around zero. In other words, even if pairs of virtual particles do pop in and out of existence, the expected average value is still near zero. But for the Higgs field, it seems to be different. Apparently, the vacuum expectation value is non-zero. The problem of false vacuum decay, in particular, is associated with the Higgs field. But what is the false vacuum in the first place? We've already established that in the context of quantum field theory, the word vacuum refers to a state where a particular field is in its state of the lowest energy, zero energy, or what's also called the ground state. In fact, because there are different fields, we can talk about different vacuums. When a system is in a vacuum state, it is stable, and in general, everything in the universe tends towards stability and tries to get rid of energy to reach a stable state. And if fields are truly in a state of minimum possible energy, and if it's impossible to lower the energy any further, then it's the state of the true vacuum. So here's a simple intermediate analogy. I'm holding a ball and it possesses some potential energy, and there's some surface. Let's assume there's nothing below it. This would be the state of minimal possible energy, and the ball is trying to reach this ground state. I'm simply preventing it from doing it by not letting it fall. So in this analogy, this is a disturbance in the field, and this is the state of true vacuum. So if you consider only the period of the ball falling, during the fall, it is in an unstable state. But when it comes to stop, it has reached the stable state. Remember that we consider that there's nothing below, so there's no lower state. But what if there's still something there? The ball falls, it stops, it appears to reach the stable state, but it actually could go lower. It still has some potential. So if this is a disturbance in a field, if down there is a true vacuum, then this state would be the false vacuum. And this is typically illustrated using graphs like this one, where the vertical axis represents energy, and here we have the true vacuum, and here we have the false vacuum. Well, what's the problem? What if vacuum in our universe isn't actually at the minimum possible level? What if it is in a state of the false vacuum? If we go back to my analogy, what if there is still somewhere to fall? And if we currently live in the universe with such a false vacuum, under the conditions of which the physical laws and constants operate in such a way that allows for the existence of the universe we know, with stars, planets, chemical reactions, and of course life. And if there is somewhere to fall, it means it can fall. And if the universe were to suddenly transition from a state of false vacuum to true vacuum, the properties of the universe could itself change dramatically, potentially leading to the destruction of everything we know, including ourselves. This is decay of false vacuum. But wait, do we even have any reasons to believe that vacuum in our universe is false and this could happen with some probability? Probably there are. I've already mentioned that there are many different fields, but there is one particular field which is often discussed in the context of the false vacuum decay. You might have guessed by now, I'm talking about the Higgs field. It's believed that when most of the known quantum fields are in a state of minimum energy, that's their state of true vacuum. Therefore, they are stable and can no longer lose energy. But when it comes to the Higgs field, things get more complicated. There is suspicion that this field may be unstable or not entirely stable. Do you remember I mentioned that unlike other fields, the Higgs field has a non-zero vacuum expectation value. The Higgs field can be in a state of false vacuum. It doesn't have a single ground state or minimum state. It can have, for example, two. So here's the true vacuum, but in reality, it's sitting here. But if you look at the shape, you can see that it comfortably stays there, rather than falling further. There's sort of a well here, and there is a barrier that prevents the field from losing energy and rolling down to the level of the true vacuum. But as I mentioned earlier, if there is somewhere to roll down to, if I don't do anything with the ball, it can remain relatively stable. But if I give it a little push. So in this state, the field can remain for a long time, but for some reason, it can overcome the barrier, and there could be several reasons for that to happen. That's why we say that Higgs field can be metastable. In other words, it has been stable for billions of years, and it may remain stable for a long time, but there is a possibility that at some point it will become unstable and go even further down the energy ladder, and then it won't be the best times for our universe. In scientific literature, the issue may also be called a problem of stability of electroweak interaction, although it's also referred to as the stability of the Higgs field. Well, let's assume we have some theoretical prerequisites for that, but do we have any reasons to believe that this could actually happen? We won't delve into the details right now to avoid further overwhelming the video, but I'll say that there are some indications. Scientists say that whether the vacuum is stable or not can be indicated by the masses of two particles. The most massive known particle, the top quark, and the Higgs boson itself, which is the manifestation of the Higgs field. The mass of the top quark has been measured with a certain level of precision, and as we know, the Higgs boson was discovered relatively recently and its mass is also known. And considering the currently known values of the masses of these two particles and some uncertainties, our vacuum could be metastable, but it could still be in the stable range as well. So at least according to this data, and if no new physics emerges, we could very well be living in a universe with a false vacuum, and that means it could transition into a state of true vacuum at any moment, if it hasn't happened already. So let's assume we do indeed live in the universe with false vacuum, but what could lead to the decay of the false vacuum and the transition of the universe into a different state? There are at least two scenarios. While our universe seems to be in a relatively stable state, to overcome the barrier and transition to true vacuum state, our universe would need a kind of a push. It would require energy. Again, let's assume that somewhere a catastrophic event occurs, so powerful, so energetic that it creates a small region that transitions into the true vacuum state. This region would start to expand and eventually engulf the entire universe. However, it would require such an enormous amount of energy that this scenario is unlikely, and the source of such energy remains a mystery. But there is another way. Two words. Quantum tunneling. Roughly speaking, in the classical sense, we imagine particles as solid balls of matter. If a particle encounters a barrier, it won't pass through it, just as we can't go through the wall. But when viewed from the perspective of quantum mechanics, it seems that at the quantum level, this is how things work. In this case, a particle can, with a certain probability, go through the barrier. This is not some imaginary process, but a very much real one, and it poses challenges, for example, in modern microelectronics. And this applies to the vacuum state as well. In other words, a universe with a false vacuum can tunnel into a state of true vacuum. And then In our universe, a small region will emerge, a bubble with a true vacuum, where the conditions are entirely different and likely different laws of physics apply. Depending on the properties and size of the bubble, it doesn't necessarily have to start expanding, but it could indeed start growing. Here, an analogy is often drawn with water, which also has metastable states that you are probably familiar with. These are supercooled and superheated liquids. On the internet, there are plenty of videos of supercooled water, which is brought to a temperature at which water normally freezes. However, if it is pure enough and left undisturbed, it could remain in a liquid state. But then, if a force is applied to a bottle, a crystallization center forms, causing all of the water to rapidly transform into ice, undergoing phase transition. A similar story happens with boiling water. You probably know that heating water in the microwave can be dangerous, because if it's superheated and then you put a spoon or something else in it, it can rapidly undergo a phase transition and boil over. When discussing the decay of false vacuum, scientists even use the same term, nucleation, meaning the phase transition of the universe into a new state starts from such a bubble that emerged due to a random event of quantum tunneling. If the false vacuum does indeed start to decay, the entire universe will not be destroyed instantaneously. If the bubble starts expanding, it will do so at a speed approaching the speed of light, gradually transforming the universe into a true vacuum state. This bubble, inside of which likely different laws of physics apply, will absorb and destroy everything in the universe. And if our universe is indeed in a false vacuum state, there is a non-zero probability of quantum tunneling. Sooner or later, it will happen. There are various estimates with a wide range. Some say it won't happen for a very long time, much longer than the current age of the universe. At the same time, given how vast the universe is, such a bubble may have already appeared somewhere. Eventually, it could reach us, Earth, the Sun, and everything else, causing their disappearance almost instantly. However, many scientists lean toward the belief that if it does happen, it won't for a very long time. And secondly, there is another important detail here. I mentioned that the bubble would expand at a speed approaching the speed of light. In my video about cosmological horizons, I said that in the current universe there are regions that are receding from us faster than the speed of light. Not because they themselves are moving that fast, but because space-time itself is expanding and they are far enough away from us. So, if an object that is currently beyond our cosmic event horizon emits a photon now, that photon will never catch up to us, and we will never see it in its current state, unless the universe suddenly decides to stop expanding and begins to collapse back, which, according to current understanding, is a less likely scenario. So if a bubble of true vacuum were to form, but so far away from us that it lies beyond our cosmic event horizon, it might never catch up to us. Therefore, if it has already formed, but it is situated that far away, we shouldn't worry too much. But if it has formed within the area of subliminal expansion, we might have another billion or so years left, but it will eventually catch up to us. And if it happens very nearby, we won't even have time to be scared. We simply won't exist anymore. But still, if all of this has sparked a new fear of an unavoidable cosmic threat, something that we can't do anything about, well, you should remember that it's not for certain that our universe's vacuum is false. Yes, some measurements do indicate that, but it's entirely possible that progress in physics will resolve this issue and it turns out that our vacuum is actually true, and there won't be any decay even in the distant future. Thanks for watching. As always, links to all of the sources are down below in the description, and if you enjoyed the video, leave a like, comment and subscribe. Bye.